Hello everyone, and welcome to this session. This session is on machine learning using the Python programming language. Python is one of the most popular languages for data science, and machine learning is something that you're going to do if you're a data scientist. This training is designed to teach you everything about machine learning. So if you're just getting started, maybe don't know anything about machine learning other than the word ML itself, that's totally fine because this training is designed for you. We'll be starting with everything from machine learning from scratch. A little bit about me before we get started. I'm myself, Sanket Sarang. I'm the founder and chief of products at BlobCity. BlobCity is a very niche company in the data science space. We also offer our very own product, which is the BlobCity AI Cloud. The BlobCity AI Cloud allows you to run your Jupyter notebooks or data science notebooks on the cloud environment. I personally started programming at the age of 10. I went on to building a social media chat app at the age of 20. I built a full-feature database at the age of 26. This database is called the BlobCity DB. It is open source. You can search for it on GitHub, and you can even contribute in the code. We still do actively maintain the product. I've been a speaker at several events, including extremely large conferences. I've trained several senior executives across several multinational organizations, and I also happen to be a mentor to startups and an angel investor in startups. So, to begin this session, let's start with understanding what is AI and ML. And I'm going to start with both AI and ML because the terms are used very frequently together. So let us understand both the aspects of artificial intelligence and machine learning. We'll also take a look at how are the two terms related to each other, or how are they different than each other. So let's get started with the term AI, and if you don't already know, AI stands for artificial intelligence. But before we understand what is artificial intelligence, do we really understand what is intelligence? Right? Let's ask us the question, what is intelligence? How would you define intelligence? Right? Simply put, intelligence is defined by 5 key characteristics. These are not the only, but these are the 5 key characteristics. And intelligence is an ability that typically living beings demonstrate, and it's mainly common in human beings, but it's common with other living species as well. So intelligence is the ability to learn, ability to perceive, reason, problem solve, and linguistics, right? The 5th one, linguistics, is very common with human beings. We talk, but it is also said that animals do talk. They have their own language of talking, but they do talk. So they do possess the power of linguistics. So intelligence is not really something that's unique to human beings. It is also available in several other living species. But these 5 characteristics is what actually defines intelligence by itself. So it's our ability to learn, our ability to perceive the surrounding, our ability to reason, problem solve, and linguistics. Now keep in mind, computers or machinery, as we call it, by definition of their existence, are not actually intelligence because they do not perceive these 5 characteristics in the natural form, right? So what is artificial intelligence? Now that we have really understood what is intelligence, what is artificial intelligence, right? Simply put, artificial intelligence is the intelligence that is imparted to otherwise dumb machines, right? Now, what does this mean? What do we mean by saying that we make machines intelligent? What do we mean by saying we make machines learn, we make them perceive, we make them understand linguistics? What does it actually mean, right? The simplest answer to this is we are making machines mimic intelligent behavior. They're not actually becoming intelligent, right? It's important to understand that machines are machines. They're not actually intelligent. They can't perceive. They can't talk, right? They can't problem solve. But they can mimic doing that. So we give them the ability to mimic intelligence. And when we do that, we call it artificial intelligence. That, my friends, is the simplest explanation of what is AI. And that is all there is to it. So did you know that you can actually see AI in several uses? Whether it's medical diagnosis, stock trading, robotic control, law, remote sensing, scientific discovery, and including some toys, they actually use AI, right? So if you buy some of those Lego kits with augmented reality built into it, that is AI. Augmented reality is some degree of AI. Being able to render an image in the real world in front of us is some degree of AI, right? Your automated cleaning bots, those small pieces of vacuum cleaner, those micro vacuum cleaners that will just pick up anything you throw on the floor, that is AI. Self-driving cars, for example, are AI. Remote sensing is AI. Medical diagnosis is AI. People use AI in stock market trading, right? And AI apparently is actually used in more places than we think, right? And Nick Bostrom, who is a very noted philosopher, he actually said that a lot of cutting-edge AI has filtered into general applications, right? And it's often without being called AI, because once something becomes useful enough and common enough, it's simply not labeled AI anymore, right? So did you know that some of your washing machines are actually AI? They use fuzzy logic, and fuzzy logic is considered a subset of AI. Right, your refrigerators at times are AI. Refrigerators especially sense that you're running out of milk, you're running out of vegetables, and they can place an order for you, is actually AI, right? But in many occasions, even simply typing on the keyboard on your cell phone is AI, right? So have you experienced this when you actually take your friend's phone and you try typing on it, you realize you're kind of mistyping the characters, right? And it's the same keyboard. It's the same make and model. It's literally the same phone, but you'll end up mistyping characters. And this happens because the phone is actually using AI to figure out what you're typing, and it's customizing the typing keys of the keyboard based on the phone's owner, right? So when you change the owner, or you take your spouse's phone or your brother's phone or your sister's phone, you will realize that it's much harder to type on that, even though it's actually the same model. Right? And this is so because the keyboard itself is using AI, right? But we don't call it AI. We just call it a normal keyboard. It's a touch keyboard, right? It's not called AI. Now that we have a brief sense of understanding of what is artificial intelligence, let's take a look at what is machine learning, right? So what is the difference between artificial intelligence and machine learning? So let's summarize this one more time, right? So artificial intelligence can be defined as intelligence exhibited by machines, right? Which is machines doing functions that mimic cognitive functions of the human mind. They're not actually intelligent, but they mimic intelligence, and that's what we call artificial intelligence. Now, what is machine learning, right? Machine learning gives computers the ability to learn without explicitly being programmed. Which means if you've giving a computer the ability to learn something, and it can then mimic intelligence based on its learning, right? But it's learning something that you're giving to it, then its ability to learn is what we call machine learning, right? It's when the machine can actually start learning from the data you give it, is the time when you call it machine learning. So the process of learning is called machine learning. So what is the difference between artificial intelligence and machine learning, right? So artificial intelligence is ability of machines to carry out tasks that are considered smart, whereas machine learning gives machines access to data, and you basically let them learn for themselves, and that is machine learning. However, is artificial intelligence and machine learning completely two different things, right? Are they really that different? The answer is no. The real answer is machine learning is a very, very small subset of artificial intelligence, right? So we often say AI and ML, and we say AI and ML because people actually use a lot of ML, right? And typically when you're using structured data and you want to do, say, sales forecasting or some predictive analysis, or you want to do anomaly detection, most of these are machine learning algorithms. So most data scientists today use more machine learning algorithms than pure play AI algorithms, for example, right? So machine learning being that prominent and mainstream, it has a real standing of its own. So you'll end up using the term AI and ML very commonly, but however, most people don't understand this, that machine learning is actually a subset of AI, right? So machine learning is not an independent thing. It falls in the bracket of AI. So when you study artificial intelligence, you do, of course, study machine learning. And when you study machine learning, you are indeed studying some amount of artificial intelligence, right? So it's important to keep in mind that machine learning happens to be a subset of artificial intelligence and not an independent term. So while you may continue using the term of AI and ML, ML comes in the bracket of AI. So when you use the term AI, it actually covers the term ML as well. Enough of theory. Now let's get started with some of the tech stuff. And we'll be covering some interesting concepts about machine learning and AI in this course, and we'll be looking at a lot of computer programming examples. Before we get to some of the examples, I want to cover some basics about various machine learning models that are there. And to begin with, we're going to start with neural networks. People usually look at neural networks as AI, which is true, but neural networks predominantly comes in the landscape of machine learning. A neural network comprises of primarily three layers. The first layer is the input layer. In between, you have one or more processing layers. So this neural network that you see has a single processing layer, but a neural network can have more than one processing layer, and then it has an output layer. All neural networks take numerical inputs. So you give numbers as input, it processes the numbers, and then it gives a number or one or more numbers in the output. Neural networks work on the concept of the human brain. They're very similar in structure to the human brain. And the human brain predominantly comprises of these neurons. And you have these neurons, and then you have the synaptic connections between the neurons. So the bulk that you see there is actually a neuron. So the circle in our neural network is actually the neuron. And then you have a connection between them, which is what was represented by arrows in our neural network. So what you see here is the circle is the neuron, and the arrows are the synaptic connections. And these are very, very similar to how a neural network works inside the human brain. Now, the simplest form of a neural network is just one neuron with two synaptic connections, one being the input connection and the other being the output connection. So the left side that we have here is the input. This is what feeds into the neuron. The right side is the output. Now, you can have several types of activation functions. So let's say I have a binary-based activation function, and I say if the value of the input is greater than 0.5, the neural network is activated. If it is less than 0.5, it is not activated. So what does this mean? It means if I give a value of 0.25, the neural network will produce an output of 0, right? Which means it's not actually producing an output, it's basically producing an output of 0. However, if I give a value greater than 0.5, it could be greater than or equal to, so 0.75 value, and the neural network will now activate, which means it will produce an output of 1, right? Which means the value passes through the neuron. Now, something like this is called a binary step activation, and it can be written by the mathematical formula, which is called f of x equals 0 if x less than 0 and 1 for x greater than 0. This is assuming if you use the binary step on the value of 0. You can also use the binary step on the value of, say, 0.5, wherein your numbers are in the range of 0 to 1. If your numbers were in the range of -1 to 1, you would use something like this. A binary step classifier is also represented by the simple graph, which means on the negative side of the x-axis, you have the y value of 0, and on the positive side of the x-axis, you have the y value of 1. And this is the simplest form of activation function for a neural network. Now, this is not the only form of activation function, though, for a neural network. So there are several types of activation functions that exist. So you could have an identity function, wherein in the identity function, the value of output of the neural network is same as the value of input. So you can see the function is f of x equals x, right? And the binary step we already saw. You get logistic, stan-h, rectified linear unit, Gaussian error linear unit, and there are several others that exist. So when you take a neural network, it's typically the job of the data scientist to decide what type of activation function you want to use. And your output might significantly vary based on the activation functions. If you were to consider a neural network that followed the identity function, then such a neural network would always fire, which means whatever you pass it as input, the same number comes as the output. So if you give 0.75 input, you would get a 0.75 output. If you give 0.25 input, you would get 0.25 output. This is exactly same as the identity function here, which basically means f of x equals x. So 0.25 input equals a 0.25 output. And if you were to give a negative number as input, you would get the same negative number as output. So there are several other identity functions that can be chosen from. And as I said before, it is typically up to the data scientist to decide which identity function to use. In this session, we won't be covering all the details of when to use what identity function because that requires a lot of time. But I wanted to show you this so that you have an idea that there are a lot of functions, activation functions, as you might call it, which neural networks have, and one has to choose the right function. So based on whether you're doing image recognition, or you're doing audio recognition, or you're doing text classification, or you're doing simple numerical processing or predicting the stock market values. So based on the nature of the data, one has to take a decision on which is the right activation function to use for the neural network. And almost all forms of neural network can be used with any type of activation function. The job of a data scientist, of course, does not end with choosing an activation function. Once you've chosen a neural network, you've chosen an activation function, you should train the neural network. You will be required to train the neural network. Now, in the training of the neural network, you might actually realize that the activation function that you've used is not really working that well for you. So if you do happen to come at the conclusion that the specific activation function is not working, then you can always change the activation function and retrain the neural network. Sometimes you might have to change the neural network itself. So when I say change the neural network, it means change the number of hidden layers. Typically, the input layers and the output layers might remain the same based on the business problem you're addressing, but the number of hidden layers can change. More the hidden layers, more the complexity, and more discrete data sets can the neural network learn from. Now, there are three different types of neural networks that one can choose from. The first type of neural network is a static neural network. A static neural network is essentially a pre-trained neural network. And the second type is a neural network that undergoes supervised learning, and the third is one that undergoes unsupervised learning. We'll be covering both of supervised and unsupervised learning in this session. Let's first start with looking at a static neural network. A static neural network is a pre-trained neural network that acts like a black box. So you give it some input and it produces an output, and this output is based on pre-trained rules, which means you already have a trained supervised or unsupervised network. And a static neural network must be trained, so it doesn't work on its own. It is either gone through training through a supervised model or an unsupervised model. An example of a static neural network is, say, the gear shifting system in your automatic transmission car. So we've all seen when we drive automatic transmission cars, the car is pretty smart in deciding when to up the gear and when to down the gear. And these decisions, while they seem very simple, in reality, they're not very simple. So the car might have to move the gear up or down based on several external factors. And these external factors could be the inclination you're driving on. So are you climbing uphill? Are you going downhill? Are you driving on a flat road? Or are you driving on a slippery road? Is it raining or is it snowing or has it just snowed? Have you driving on ice? Or what is the level of acceleration you want, or how hard are you braking? All of these are variable parameters which are, some of them are in the driver's controls while some of them are not in the driver's control. And the car has to take the decision on when to shift the gear up and down based on several of these inputs. Now, this is a neural network which is inside your car. However, you consider the gearbox system to be just a simple machine. And this goes back to the statement that Nick Bostrom made, which says if something is that common and that mainstream, we do not call it AI anymore. However, the simple gear shifting system in your automatic transmission car is actually AI. If you look at it, the traction control, the dynamic stability control, some of these features that you get in advanced cars or luxury segment cars, they are also AI based. They are not based on exact science and rule sets. They're based on artificial intelligence, and they're pre-trained systems, which means they're statically programmed neural networks which are residing in your car, and they're put into the brain of the car. So most modern cars come with a computer, and the computer controls several functions in the car, and that computer comes with a pre-trained neural network to understand what the car should do based on several externalities. Next, we'll take a look at supervised learning. And supervised learning is one of two types of learnings for a neural network. In case of supervised learning, you have input data, which is fed into the neural network, and the neural network produces an output. This output is now checked against reference data that you have. So the output has an error estimation, and the neural network can basically look at how the output varies from the reference data. So more the deviation from the reference data, the more is the error. The lesser the deviation from the reference data, the neural network has done the right job. So the neural network can compare its output with the reference data that's provided, which is the reference output, and it can take that feedback, which is the training loop, and learn from that training loop to reorganize its weight matrix. So it can reorganize the activation functions of several of its neurons, and sometimes even the synaptic connections between neurons, to then figure out what is the exact right combination of the neural weights to have, so that the input gives the desired output. Now, this is not done with one data point, but this is actually done with thousands and thousands of training data points that are given. So when the neural network tries to change itself for any one data point, you might get another data point not satisfied. So it's pretty common practice that it kind of has a bias towards certain conditions. So it works in certain conditions but doesn't work in other conditions. And this is why the neural network training function will typically try to do an error minimization or a deviation minimization, and it will try and come out with that specific set of combination that has the least possible error across all of the data points that you have fed into the neural network. If not for supervised learning, the other option is unsupervised learning. And as you can see, in unsupervised learning, we do not have any reference data being fed into the neural network. So the neural network takes data, it produces an output, and it basically learns from the output itself. So what this neural network is trying to do is it basically tries and understand how different is your input. So when you change your input, it tries to change the output in the same proportion as you've changed the input. So it is trying to basically bring in consistency between small deviations in input to small deviations in output. If a small deviation in input makes a very large deviation in output, then we say that the neural network is actually untrained. So an unsupervised learning neural network cannot be used to derive any specific desired outputs. So it's totally up to the neural network to come up with the output. And typically these are clustering algorithms that allow us to understand patterns of data, and such neural networks can be used to extract patterns of data that are not visible to the human eye. So such a neural network can essentially start clustering our data into groups of similar types of data, and it can tell us how many different types of data are present. So many unsupervised learning neural networks are primarily used for data discovery or understanding patterns of data which are otherwise not visible to the human eye. Before we move further, I want to quickly take 2 minutes to cover deep learning. And it's a common misconception that deep learning and neural networks are two different things. In reality, deep learning is actually a neural network. So when you use training for a neural network, which can be unsupervised or supervised, both learning models are fine. And if you use these training algorithms on a neural network that's substantially large, then we call it deep learning. So the size of the neural network makes it deep learning or training a normal neural network. So the difference between a deep learning neural network and a normal neural network is simply the number of hidden neurons in the hidden layers. So typically a deep learning neural network, as you can see here, will have substantially large number of neurons and substantially large number of synaptic connections across these neurons. And there is no exact definition of what is large and small. It's just based on the specific use case. If your network is comparatively large as compared to other neural networks that you use, then we call it that this network is a deep learning neural network. Now, because of all of these synaptic connections that you have, training a deep learning neural network can require significant amount of compute power. It's not an easy job to train this network. The algorithms that you use for deep learning training are very similar to the algorithms you use for normal neural networks. They're actually the same algorithms. So you can use supervised or unsupervised in exactly the same algorithms. However, it takes a lot longer to train a deep learning neural network because there are a lot of variables. Also, because of the large synaptic connections, deep learning neural networks can learn more things than smaller neural networks. These networks have the capacity of storing more information and handling more complexity than simple neural networks. So in many scenarios, if you're using deep learning, you will most likely use graphic processing unit to accelerate the training of your deep learning networks. So GPUs give you massively parallel processing tasks with thousands and thousands of parallel processors, unlike the CPU, and these parallel processors basically help you train a deep learning neural network faster. Now that we've understood a little bit about neural networks, let's look at some other machine learning models. Did you know that neural network training is also actually machine learning? So when you train a neural network, you're essentially doing machine learning. So neural network training is a subset of the broader term of machine learning. And any training that you do for a neural network is effectively machine learning, because you're training a machine to understand something from your data and then behave based on the training that is given to the neural network. Now let's look at two commonly used ML strategies, and these will be classification and clustering. Classification comes into the category of supervised learning, whereas clustering comes into the category of unsupervised learning. So simply put, in classification, we can have like linear classifiers or nonlinear classifiers, and we are telling the classifier what data points are there. So you can see the plus and the squares. So we are telling it what is a plus and what is a square, and then you want to basically derive that red color line that you see, right? And the red color line is your classification point, or you can also call it a support vector, and this is a linear vector, wherein you say that anything above this line on one side of the line is a plus, anything on the other side of the line is a square. And the same thing can be done even in a non-linear manner. So the graph on the right side shows you a non-linear classification. Clustering, on the other hand, groups items together, and then it gives these colors, right? So you can see that there's a color 0, 1, 2, and 3, and you can have these various colors of red, blue, green, black, and these colors basically are different logical clusters. Now, clustering is unsupervised learning, which means we do not have control over these data points. So we do not know what the 0 color means here, or what the 1 means here, or the 2 or the 3 means here. We do not know what that means. But the neural network or any other machine learning clustering algorithm that you use can basically create these clusters and say, I can actually find these items to be very similar to each other. I don't know what they do, but I can find that they're very similar to each other, right? And this is an example of clustering. On the other hand, going back to classification, which is supervised learning, you are explicitly telling the neural network or the ML model exactly what is what. So it knows the difference between a plus and a square, right? And it very clearly knows the difference between a plus and a square. But in clustering, that difference cannot be known. So by now we know that classification is supervised learning and clustering is unsupervised learning. At a fundamental level, we have understood the difference between the two. But let's look at it a little further to understand classification and clustering better. So let's take some real examples to see where you would use classification, and another example to see where you would use clustering. So here is an example of a classification model. Let's say we want to identify fruits from an image. So we've been given images of fruits, and we want to identify which fruit is present inside the image. So I would use a classification model, and I would use a trained data set to train my classifier. So let's say my data set comprises of apples and oranges. So if I feed it an orange, I need my classification to recognize it as an orange. Now this classifier can do, because for the classifier, I'm going to give it an input of a set of images, and I'm going to tell it which image is what. So I'm actually telling it that this orange is this orange in color, it's round, it has that leaf on top, maybe it comes without the leaf. An apple is this similar round-shaped fruit, but not so round, but it's predominantly red in color, not orange in color, right? And I'm giving it this training data, so the classification model during the training process can learn from this data and then classify it and recognize it as orange or apple. And this is the simplest understanding of a classification model. On the contrary, a clustering model cannot actually identify an orange and apple for you. It simply cannot do that. This is so because clustering is unsupervised learning. So there is no way for the clustering model to actually know what data you're giving it or what you expect out of it. It simply cannot know it. More so, it cannot know your nomenclature. So when I say nomenclature, I mean the name apple, the name orange, it's a nomenclature. Clustering models cannot understand nomenclature. They only understand similarities between data. So in this case, if you give it a yellow squash, it can basically recognize, a clustering model can basically recognize this fruit as maybe an elongated yellow fruit, or simply a yellow fruit, or anything, or specific shape like a long one or a rectangular one. It can recognize that, or it can recognize the color yellow, or it can recognize the shape. But what it cannot do is it cannot recognize this as a yellow squash, because the word squash, or for that matter the word yellow, is not something the clustering model will understand, right? And this is because there's no training provided. You simply put a lot of data, you pass it through, and you expect the model to self-train. So when it is self-training, it's simply looking at all of the data and segregating this data into logical clusters. So if you give it a lot of squashes and apples and oranges, it might be able to cluster apples in one bucket, oranges in another bucket, and squashes in another bucket. It might be able to do that. And you might have to look at the data and figure out which is what. Or on the other hand, it could also put all the squashes in one bucket because they are elongated fruits, and it can put apples and oranges in one bucket because they are circular fruits. Now, as a data scientist, you will have some degree of control on the clustering itself. So you can instruct it on what type of clustering you want to do, whether you want to do clustering on color, you want to do clustering on shape, or you want to do clustering on both color and shape. This you can define as a data scientist. But you cannot tell the clustering model what an apple is and what an orange is. So it won't be able to distinguish between the two directly for you, because you're not giving it labeled data set, you're not teaching it nomenclature, and there's simply no way to do that in case of a clustering algorithm. We have covered a lot. So let's take a pause here. Let's take a moment to look back and see whether we remember every single thing we've covered in the training so far. I've gone through a lot of slides, we've covered a lot of theory, and if you might remember, this session is about machine learning using Python. It's not about the concepts of machine learning. So let's now move to some programming. We looked at clustering, we looked at classification, we looked at the basic principles of classification and clustering. I would like to mention that the classification and clustering models that we saw here with the apples and the oranges and the yellow squash, these can be done on neural networks as well. So we began with looking at neural networks, and then we looked at what is clustering and classification, which are two commonly used machine learning models. And now in the rest of the session, we are actually going to practice some programming in Python. So in this session, I want you to follow me along in the coding. So it shouldn't be that I'm just showing you the code. I want you to follow along. And as promised, we're going to give you all of the cloud resources you need to follow me in the coding. So we're going to give you ready code, and we're going to give you compute infrastructure on the cloud, totally free of cost, for you to follow me in the coding session. So it is now time to open your BlobCity Cloudbooks. And BlobCity Cloudbook is part of the BlobCity AI Cloud product, which is a premium offering of BlobCity that allows you to run Jupyter notebooks on the cloud at scale. And we have a free plan, so you're going to use the free plan. All you have to do is register. You don't have to pay anything at all. Just choose the free plan. One private cloud book is included free of cost for life. It's not a trial. It's a permanent free plan, so you can keep using it after the session as well. So I want you to follow the link in the description to open up your CloudBook. So look at the link in the description, and it'll say copy your CloudBook from here. Basically take that link, pick it up, open it, and start and hit the copy CloudBook button. I'm going to show you in a bit how this is done. So to set up your CloudBook, you're basically going to follow 5 simple steps. And I've kept a countdown timer running for 5 minutes. So 5 minutes is all it's going to take to set up your CloudBooks, and that's all we really need here. So I strongly encourage you to do so because it's going to really help you follow me in the coding. And there are a lot of example code projects that you will receive, which you can also practice after the training. So step 1 is follow the link in the description of this video. Second is once you open this link, hit the copy CloudBook button. If you are a registered user, then you can simply log in. And if you're not a registered user, then please do register. You will have to set up an account on BlobCity to access your CloudBook. You will receive an email to set up your password. So if you're not a registered user, you can just simply type your name and email. Make sure you type your email correctly. You will receive an email notification with a link where you can set up the password. And once you've set up your password, log into your BlobCity Cloud, open the link in the video again, and this time you will see a copy CloudBook button. So I'm going to show you how this is done. So I have my account open here, right? And my account basically is already logged in. You can see I'm logged in as Sanket Sarang. And I've opened the link that's in the video description on my tab here. So you should see a page like this, which says the name of the CloudBook is Machine Learning with Python. It's a SciPy notebook, Jupyter notebook title, and it's CPU based. And you will see this copy CloudBook button. Again, if you're not a registered user, you will see an option on top to register or log in. So I recommend you register, log in. Once you're logged in, then you hit the copy CloudBook button. So at this point, I'm going to hit the copy CloudBook button. I can give a name to my CloudBook. So I can say my ML CloudBook. And I can make this my first ML CloudBook if you so desire. And then you set up a password for your CloudBook. So I'm going to set up a password here. And this password is unique to your CloudBook. This is not your account password. So each and every CloudBook can have a unique password of its own. And you can share this password with other users along with the link of your CloudBook. So this is the security measure. If you do forget the password of your CloudBook, unfortunately, there is no way for us to restore it. So I strongly recommend you remember the password or write it down or save it in your browser or somewhere and keep. So once I've given a name to my CloudBook and I've hit a password for my CloudBook, I'm actually going to type this again just to be sure. And I can hit the copy CloudBook button. So when you hit the copy CloudBook button, you will see a progress bar on top. It should now copy the CloudBook for me. And you can see I have my first CloudBook copied. I have my ML CloudBook. This was created from the CloudBook that is provided to you as a reference. At this point in time, I'm going to simply hit the Open CloudBook button. And when I hit the Open CloudBook button, this will actually boot up the Jupyter notebook in the background. So it's going to start the CloudBook for me. And once it's started, it's going to show me. So you can see this is a common practice. You do land up with a pop-up blocker. So I'm going to click the icon here. So if you have a pop-up blocker on your computer, which I do have, you might also see a similar icon. You should actually allow the website to give the pop-ups. It'll open and then it comes with my login page. Now, this is the page for my CloudBook. So this is where I hit the Open CloudBook button. After it's open, it comes to this page. Here I have to enter the password not for my BlobCity account, but the password for my CloudBook. So at this point in time, I'm going to type in the password. And once I've done this, it's going to log me in and I have my CloudBook. And you can see we have a bunch of folders here. We actually have a lot of project examples provided to you. We won't be going through these, of course, but you can utilize all of these in your own study after the session. In this session, we'll be primarily looking at some of the classification examples. So we'll go into classification. and we'll also look at clustering. So I'm going to wait here, give it the other 25 odd seconds for everyone to finish opening the cloud books. If you've not done so yet, you should do so now. This is a cloud tool. It's free for life. One private cloud book of yours is completely free for life. You can use it for as long as you desire. We also give you access to GPU if you so need on paid plans. So get your cloud book spinning. Now is the time. If you've not yet opened it, I recommend you pause the video and resume later. It is now time to get your cloud books opened up. So if you've already opened your cloud book, you should see a page like this. You should see all of these folders. These are various types of example projects, and we have taken all of this from scikit-learn. I'm going to go into the folder called classification. So this is the folder that we're really looking at. You don't have to tick this folder. I'm just ticking it to mark it and highlight it. So we can click the folder name to go into the folder, and there are several classification examples here. Today, we're going to specifically look at the digits classification. So I'm going to click on the file, and it should open the file for me. The digits classification simply does classification of handwritten digits, which means we're going to train a classification model to understand digits that are handwritten. And by digits, we mean numbers. So numbers can be anywhere from 0 to 9. So we are only looking at digits from 0 to 9. And we want to classify these digits based on known data. So we will basically be using a supervised learning model, which means we have a data set of all the digits that we want to really look at here and classify. And then we have a bunch of other digits that we don't know what their values are, which means that's unknown data. And then we will predict what these values are for the unknown data, and then we will compare how accurate the classifier is. So the whole program is split into 9 logical steps. Step 1 is we import the necessary packages. So we can click the button here to run and move on to the next cell, and you can see that my highlight changed to the next cell. Now over here, I'm going to import matplotlib. I'm going to import matplotlib.pyplot as PLT. Then we're also going to take the sklearn packages. And from sklearn, we're taking data sets, SVM. So SVM is support vector machines, and metrics. Metrics is used for some analysis that we do. And then we're also looking at the sklearn and model selection, and import the train and split package, which allows us to split and train this data across multiple data sets. Now, as we move ahead, we're going to start loading this data set. So I'm going to run through this cell, and you can see that there will be a cell number that shows up here. This shows me block number 1, which is the logical block. And it printed an output saying automatically created module for IPython interactive environment, which is fine. I'm expecting that, so it created it. The next step is actually loading a data set of images. And we don't have images in files. We're not going to take files. We're actually going to use a data set given by scikit-learn. So scikit-learn has multiple data sets, and some of that being digits, handwritten digits. The most common other data set that's used is the iris data set. And iris is actually a data set of flowers and petals. So in this example, we will take a data set of handwritten digits. So all I have to do is I have to say data sets.load digits, and that should load all the digits into this variable for me. Right? Keep in mind that I imported data sets from sklearn package, and that's where the data set is actually defined. I'm simply loading it and assigning it to a variable. So let's run through this, and this line is executed. The next step is to create a labeled collection. And what we mean by labeled collection is we need to create known data points. So for any particular image that we have in here, we want to know what that image corresponds to. So if you're looking at a digit of 0, we want to know that this handwritten digit actually belongs to 0. So that is the labeling part. So we use labeled data set for supervised learning because in supervised learning, we expect the model to predict an output, and then we tell it what is the correct output that it should have predicted. And it can use the correct output and understand the deviation and go back and retrain itself to start computing, to start readjusting everything to come up with the correct output. So since this is a supervised learning model, we will be taking a labeled data set. So I'm just going to go through this, and I'm going to extract the digits.images and digits.target. So digits.images are my actual image files. Digits.target is what is the digit that this image file corresponds to. So there's a target value associated with each and every image. This is provided to us by scikit-learn, so we're not doing anything here on our own. This is a pre-labeled data set, right? And we're just creating into a list of images and labels. So I'm going to run this through, right? And you can see it basically created, you can see how these digits actually look like. These are handwritten. So you can say this is a 0, this is a 1, this is a 2, and a 3. And it printed some of this stuff out because we asked it to print, right? And you can take a look at some of these digits. You can see that these digits, like the number 2 here, is not how a computer would print it. This clearly looks like it's handwritten. You can also see the number 3, it's a little crooked. Right, this data set is produced by handwriting of several different individuals. It's not from one individual. So there's a plethora of combinations in which the same digit is written. And at a pixel level, this is how the digit looks to the computer. So we kind of scale them into an 8x8 resolution, and that's primarily to kind of shorten the data and also make it more manageable. So we are scaling these images down to an 8x8 resolution and then looking at it. Now, moving further, we have to do a process of pre-processing the data, or as we call it, flattening the data. So we're basically going to take the number of samples, and then we're going to take the array of images and basically reshape them. So reshaping them makes them more manageable to feed into a classifier. We're not changing the data here. We're not touching the data. We're just reorganizing the arrays to make it more manageable to feed it into the classifier. The reshape comes from NumPy. So it's a function from NumPy which we're using here. So I'm going to move this through. And you can see I actually put a print line here. So I want to see the number of samples. So I can actually say n samples is equal to length of digits.images. So this is telling me that I have 1,797 images in my data set. Now this is correct because the sample data provided by scikit-learn has 1,797 labeled images, which means these are handwritten digits, and we have 1,797 of them, and we already know what digit they correspond to. So all of this is pre-labeled data set. The next step is to create a classifier. And we are going to use the support vector machines classifier, inside that the SVC function, to create a support vector classification. And we're going to use a gamma value. The gamma value is actually a parameter for nonlinear hyperplanes. So basically, the higher the gamma value, it tries to exactly fit the training data. And if you have a very high gamma value, you will lead to overfitting. If you have a very low gamma value, it will lead to underfitting. In today's session, we won't be covering all the details of how the gamma value is selected. But keep in mind that if the higher the gamma value, the more exact fit it will try to do. However, you cannot overfit it or underfit it. Both overfitting and underfitting have a problem. So we're just going to run this through, and it's going to create the classifier for us. And you can see that the line number 5 came in here. And this classifier is basically created on the gamma value of 0.001. We have not yet provided any data to the classifier or trained the classifier. We have not done that yet. We will do that in the following steps. The next logical step for us is step number 6. And in step number 6, we are going to train and test the data, which means we are actually going to create 2 separate data sets. And the training data set is the one that we will feed to the classifier, and this will be a labeled data set. And this labeled data set will allow the classifier to learn about our data, and then it can start adjusting itself to kind of understand data whenever we wanted to predict what the value will be. The test data is actually used for testing if the classifier is properly trained or not. Now, you can decide how much data you want to take for training and how much data you want to take for testing. So in this case, we have actually used test size equals 0.5. So test size can be anywhere from 0 to 1. It can be any value from 0 to 1. When you take a value of 0.5, you're essentially saying that 50% of my data, I want to take it for testing. So it will take 50% of this data out, and it will not feed it into the classifier for training. So one fundamental mistake that many people do is they train the classifier over the entire data and they also test it over the entire data. This is a bad practice. It might work in principle, but it's actually a very bad practice. If you really want to test the classifier, then you want to test it on data that you have not trained it with, which means you take data which is different than your training data set. So it's a common practice to kind of split your data into a train and test data. And this function allows us to do a train and test split. This function also comes from the scikit-learn package. So if you go up, we can actually see we did import this model. So we did import a train and test model, and that is where that function is coming from. So this will basically, given the data that we have, so we are basically providing it the data, we are providing it the target values, which is each record in this data corresponds to actual what value of output. This is the classification itself, because this is known data and we are using a supervised classifier. This is instructing how many data points I want to keep for testing and how many for training. And then the last parameter is shuffle equals false. Now, in this case, what shuffle does is I can choose to shuffle these data points, which means I don't want it in the ordered manner. So I can shuffle it and then split it up, or I can choose to not shuffle it. In our case, in case of digits, it really doesn't matter if we shuffle or not. But in case of, say, if you have stock market data or any time series data, then you definitely do not want to shuffle. So in that case, you would say shuffle equals false. But in this case, which are fairly independent data points with fairly independent images, it really doesn't matter whether we shuffle or not. We've just chosen shuffle equals false because it saves us some time in shuffling the data itself. So what this essentially means is out of all my data points that I have, out of 1797 data points that I have, it'll choose 50%, the first 50% of these data points for training, and then the next 50% of these data points for testing. Had I made this 0.7, it would have been a different proportion, which means I would use 70% of my data for testing and only 30% of my data for training. If I did this 0.3, then that would mean I would basically use only 30% of my data for testing and 70% of my data for training. It's actually with extremely large data sets where you have like tens of thousands of data points or millions of data points, it's a common practice to use only 20% of your data for testing. So you typically take 80% of your data, put it into training, and then you take 20% of it and use it for testing. So this is a common, 0.2 is a common practice. It's a very, very common practice. On rare occasions, especially with very large data, you might use 0.1. But in our case, we don't have a lot of images. We are just looking at 1,700 odd rows. So over here, we'll actually do 50-50. We'll take 50% of the data for training and 50% for testing. So the next logical step is actually once you have this data split up, so you have the X train and the X test, and the Y train and the Y test. These are actually split up, right? So on what? So the X train and the Y train are the training data points. X test and the Y test are the testing data points. Right? And we're going to go through this, and the next step is actually to train the classifier. So to train the classifier, we already chose the classifier. We have not defined the classifier here, right? The classifier comes from here. So this classifier is just a variable. This variable is assigned to svm.svc. The gamma value is set to 0.001, and that is my classification model. svm.svc comes from scikit-learn package. Now I take this and I say classifier.fit. Now, depending on how much data you have, the compute power of your server, all of that, this function call can actually take a long time. Sometimes it can take a very, very long time. So it could be several minutes before you get an output. Now, in this case, the data is not too large. Plus, we are using a server that's really powerful. So you can see it really happen very, very quickly. It says SVC, this is training is complete, and gamma was set to 0.001. Right? Now, at this point in time, we have a trained classifiers, which means this classifier is completely trained and ready for our use. Now that we do have a trained classifier, let us test it to see how good the training is. So the next step, which is step number 8, is to test the classifier. And to test it, we're just going to basically call classifier.predict. And we're going to get our X value of testing, and it's going to essentially produce a predicted value, right? And we already have a Y value of testing. So the Y value of testing is actually my labels. So this is my target value, which is the Y test is my correct answer. and the predicted is what my classifier found out to be. So if my predicted value is not same as y test, then my classifier went wrong. Now, on some occasions it might go wrong, some occasions it might go right. So at any point in time, we really want to figure out what is the accuracy of testing. So now that I've predicted this value, so I'm just going to run through it, and at this point it is predicted. Keep in mind that predicting values is actually a very, very less compute intensive task. So training is always more expensive than testing. So for testing, you don't really need a lot of compute, but for training, you can need a lot of compute based on how much data you have. Right? Now that we have the predicted value, let's actually look at how good is the predicted value. How accurate are we? Right? Did we actually do the right thing or the wrong thing? So we're going to do some bunch of operations here to kind of just manipulate the data a little, and I'm going to take the images and predictions. I'm going to create a list from it, right? And I'm going to basically take it with the zip it with the original data as well as the predicted data, and pass it through some functions, and what I get at the end of it is a classification report. And that's exactly what I want to look at. I want to look at the classification report. So this is just plotting the data for me, essentially in a tabular form. So I'm going to run this through, and you can see that we have a classification report. It says the same SVC, gamma 0.001. The final values that I'm interested is in this. So over here, it gives you the precision of each of the digits. So you can see the number 0 had a precision of 1.0, which means it was almost always predicted correctly, right? And this is the training precision. This is the recall precision, 0.99. And I'm basically looking at all of this data. But essentially at a high level, if I want to look at what my average is, so my accuracy average is 0.97, which is 97% accurate. And you can look at this table and you can figure out that we are consistently 97% accurate across the accuracy, macro average, and the weighted average. So all three over here are 97% accurate. The 97% accuracy in handwriting digit recognition is actually a pretty good accuracy. Because what this means is if you give the system 100 digits to classify, it will only get 3 digits wrong, which means 97 out of 100 digits, it would classify them correctly. So we can see here that the classification is actually very accurate. However, if you want to go a little further and look at what is the inaccuracies in the classification or what got classified inaccurately, then we can print something that's called a confusion matrix. And a confusion matrix tells us how confused our classifier is. So I'm going to run this cell through, right? And we have a confusion matrix that got plotted. It's plotted immediately. It got plotted as soon as I click the button. And this is the confusion matrix in the raw system. Here we have actually just plotted it for better display, right? Now what this confusion matrix does is you can see that over here I basically have my true value or the true label, and here is my predicted label. So the true label is the actual value that the data should have been classified into, and the predicted label is the predicted value that it was supposed to classify into. So technically, for a true label of 0, I should have a predicted label of 0. So if for a true label of 0, I have a predicted label of 0, the classification is correct. So over here, I can see the number of digits that I tested against. So this cell that shows 87 essentially means that 87 times the number 0 was correctly classified as the number 0. But if I go further down in this row, you can actually see that the true label 0, which means the number was actually 0, the digit was actually 0. But on one occasion, which is here, I can actually go down further and see on one occasion, 0 was predicted to be value 4, right? So somebody had written a 0, but the system thought they had written a 4. So this is clearly an incorrect classification. But on 87 occasions, 0 was classified correctly, and on one occasion it was classified incorrectly. Now, if I go further and I look at the number 1, right, so this is my true label, and then this is the predicted label. So if I look at the true label of 1, I can see 88 times it was classified correctly. But if I go further down in this row, we can see that the number 1 was classified incorrectly once as the number 2. It also happened to classify incorrectly as the number 8. And it is also incorrectly classified as the number 9, right? So 8, 9, and 2. So it was incorrectly classified as 2, 8, and 9 only on individual occasions, but 88 times it was classified correctly. So this is what the confusion matrix tells us. So a higher value along the diagonal is actually good. If you don't get higher values across the diagonal, that's a problem. So if there's any deviation here, that's a problem. So higher values in the diagonal is extremely good for a confusion matrix. The most ideal form of a confusion matrix would be values on the diagonals only, and then everything else apart from the diagonal is 0. So that is the absolute desired outcome. So if everything on the diagonal is 0, everything other than the diagonal is 0, then you have a perfect confusion matrix. And a perfect confusion matrix means you have a perfect classifier, and perfect classifier means you have 100% accuracy of classification. However, in most scenarios, unless your data is really, really simple, you're never going to get to 100% accuracy of classification. So this confusion matrix that you're looking at is actually one of the best confusion matrix. So this is reasonably accurate. In several scenarios, you will notice that these matrices don't really work that accurately. But interestingly, let's look at a few other points. So you can see the digit 3. And if I'm looking at the number 3, and this is the true label for 3, then you can see that I have a number 5 in here. And this 5 is really concerning, which means on 5 occasions, the number 3 was interpreted as the number 8, right? And this seems right because the number 3 does look similar to number 8. And depending on how people write it, especially if they write a crooked 3 or with those extra lines, then it can get inferred as the number 8. So we can see here that the number 3, if you go along the line, you look at on 5 occasions, the system predicted the number 3 to be number 8, right? And similar problem, like the 3 was also on 4 occasions inferred as 7. And the 3 was also incurred as the number 5. And you can look at these digits are actually pretty similar looking. So based on how shabby the handwriting is, the system can interpret this the wrong way. So good. So now that we have run through this, we've actually seen how the whole prediction works, how the accuracy works, and we have actually built our first classification model. And our first classification model has been very accurate. I recommend that at your own time, you do change the gamma value because the gamma value determines the nonlinear hyperplanes. And as I mentioned, we won't be covering those in this session, but it's something you can just play around with. I want you to change this value to say 0.01 or 0.001, or sometimes you can even put a value of 0.1. And I want you to play around with it and see how it goes, how your accuracy of prediction changes, whether you're overfitting, underfitting. You can take a look at all of that. So do play around with this. As a data scientist, everything else in this program is pretty straightforward, but this gamma value is something that you will have to control. So you might have to play around with the gamma value to get your 97% accuracy. I can assure you if I change the gamma value, it's not going to be 97%. And I want you to give this a try and find it out for yourself. Now that we have seen a classification example, let's take a look at a clustering example. So I want you to open the root directory of your CloudBook again. So just close the current tab, open the CloudBook tab, and go back to the root directory. So over here, instead of classification, this time we will look at clustering. So we're going to take the clustering package. Again, you do not have to click this. I'm just showing this for highlight. So if I go into cluster, there are several clustering programs that you can see here. And we're going to take a specific program which is called the plot coin segmentation.ipynb. So we're going to take a bunch of Greek coins, and these Greek coins are loaded in an image. So it's an image of Greek coins. And our job is to do clustering on this data to extract all of the Greek coins from the image. So we don't want the background. We want to extract simply the coins. So I'm going to click this and I'm going to open this. I want you to do the same so that you can follow along. The name of the file is plot coin segmentation. So inside clustering, go to plot coin segmentation, open it up, and we will follow this file for the training. So over here, we're going to use two clustering algorithms. These clustering algorithms are the k-means clustering and the discrete clustering. Now, these both will give slightly different and varying results, but we're going to look at each of them. Again, in this file, we have step-by-step operations, and this program takes 7 steps. So we're going to be at the 7th step, we're going to apply clustering, and then we're going to look at the final results. Because this is not a classification model, which means we do not have a train and a test data, there is no concept of splitting the data between a training and a testing. Clustering is not an exact science, which means we can tweak these values and see what the data looks like. So after we have created clusters, the only thing we can do is look at the data with the clusters. There's really no testing. So we have to rely on visual inspection to see if the clustering has happened correctly. So the computer can't tell us the accuracy of clustering. There's no way it can, because there's no right clusters. We only have to see what the desired output is, and we have to humanly inspect the output to see if we have actually got the desired output. So let's start with step number 1. And step number 1 is simple loading of imports. But in the case of clustering, we have a lot more imports than we saw in classification. So here we are importing time, we are importing NumPy as NP, we're also starting matplotlib inline, then we're looking at from distutils, we're taking loose version, then we're taking a Gaussian filter, the matplotlib pyplot libraries as PLT, we're taking skimage. So in previous case, it was sklearn. In this case, because it is image data, we're taking skimage. And then from skimage.data, which is the data sets available, which are image data sets available, we are importing coins. Then we are importing rescaling function from skimage.transform. Then you can also see we are doing an sklearn.feature extraction. So this is an sklearn package. Inside this, we're doing feature extraction, and we're doing sklearn.cluster, and we are doing spectral clustering, and the feature extraction is on images. So we're taking import of images. So these are the bunch of imports that we really need for this program. And in step number 1, we've just imported all of the values. So I'm going to hit the run button to run through this cell, and you can see it says automatically created module for IPython interactive environment, and it has done all of my imports. Then as far as the loose version package goes, the loose version takes optional parameters. And these parameters were included after version skimage 0.14. So if you're using skimage 0.14, you can put these parameters for anti-aliasing as well as multi-channels. So these packages allow us to process the images. It's kind of pre-processing of the images before we do the clustering. So anti-aliasing can basically reduce the aliases between pixels to smoothen out the image a little, or smoothen out the curves a little on top of the image. So these parameters are kind of totally optional, but if you provide them, you will generally get better results. It's not necessarily that it's these parameters. There are several other parameter options also, so one has to choose from which optional configurations that you want to really use for processing your images. The next logical step after processing, after the optional configuration, is you load your data. So I'm going to run through this step, and this is just creating the rescale parameters variable for me, right, with the value. And over here on step number 3 is where I actually load my data. So I'm going to call the coins function, and this coins function came from my import. So I said skimage data import coins, and this is where I've got my coins function. Now I'm going to take my coins function and assign it to orig coins or origin coins, and what this orig coins is going to do is it's basically going to load all of these coins as a NumPy array, right? And I'm going to run through this, and I can see that this orig coins are there. If you want to look at the structure of orig coins, you can actually type in a print operation here. So you can do print orig coins, and we're going to see what shows up. And you can look at that we got this two-dimensional NumPy array. So we can actually see that this coins data is encoded into pixel data points, and all of these data points are grayscale values, and these are values of the gray value intensity of the pixel. So this value can go from anywhere from 0 to 255, 255 being the color code for white, and 0 being the color code for black. So if that pixel is black in color, the value will be 0. If that pixel is white in color, it will be 255. Anywhere between that is various shades of gray. So 126 is exactly half gray. So it's half black and half white, which is the exact mid shade of gray, right? All others are essentially shades of gray, unless it's purely 0 or 255. Now moving on from here, now that we have seen this, the next step we're going to do is we're going to actually smoothen the image a little, and we're going to use a Gaussian filter for smoothening. And there are parameters that you can have. So you can have a sigma parameter, which controls what level of smoothening you want. And you can play around with this and see how your output varies. So depending on to what extent you smoothen it, you might get better accuracy or worse accuracy. Now, after this, we are also going to reduce the size of the image by, we're going to actually reduce the size to 20% of its original size, which means we're shrinking the image. Now, this we are simply doing because it's kind of faster to do clustering on a smaller size image. If the image was very large, it would take a longer period of time. So you don't really have to reduce the size of the image. So the step number 2, which is the rescaled coins, this is totally optional. You can choose to operate on the smoothened coins itself if you want, or you can choose to operate on the rescaled coins. This is totally your call at this point in time, right? So moving on, I'm going to perform this operation, and you can see that the Gaussian filtering and the rescaling happened really quickly. These operations typically will not take time to perform. The next step is you convert this image to graph, and this is essential because this graphical data is what we are actually going to use in the clustering algorithm. So it's a simple line of code which says image.image to graph, and I take these rescaled coins and I convert them into graphical data points. So once I've run through this conversion, I basically adjust the gradient. This gradient adjustment allows me to basically control what beta value I have on the gradient aspect. So you can choose various types of gradient values. Over here, in this case, the function that we have written, this is np.exponent, which is we are actually using an exponential gradient function. And in this case, the smaller beta is the more independent the segmentation is of the actual image. And for basically controlling what level of segmentation or what level of gradients do you want, which is a tolerance level inside your clustering, you can configure in this. So I strongly suggest you kind of play around with these beta values. You play around with the EPS values, which is epsilon values. You can play around with this, try different functions than exponential functions if you so desire, and see how your output varies, right? It's a good idea at this stage to kind of play around, experiment, and then see what is the effective result on the output. As a data scientist, you are typically required to take these decisions, right? So as you can see, neither the classification nor the clustering are kind of automated. So if there were ready codes that did all of this, we wouldn't need data scientists. So it's typically the job of the data scientist to look at the data that you have, look at what you want to achieve from it, and then decide what type of functions you want to use. So if you don't want to use an exponential function, you want to use some other function, then as a data scientist, it's your call to take, right? Including the value of beta, the value of epsilon, these are your calls to take. So as a data scientist, you have to really look at what values you want. So I've taken the value of 10 and 1 raised to the power minus 6, right? And I'm going to go forward with this, right? We're not going to explain the mathematics behind this inside this session. It would take a while to kind of explain that. So let's move on now to the clustering aspect of it. And if we go to clustering, here we want to actually cluster this image into a certain number of regions. So you have to tell the system on how many independent clusters you want to create. So in this case, I want to create clusters of 25. So I want to create 25 individual regions, and that's what my clustering algorithm will do. Keep in mind that we do not have a training data set or a testing data set. Like in the previous case of classification, we had a training data and a testing data, and we took this whole data and we split it into a train and test. We trained the classification algorithm with the training data, and then we tested it with the testing data to predict accuracy, right? In this case, there is no such thing possible. In this case, all you're saying is on my image, I want to identify 25 independent clusters. These clusters are basically pixels that are similar nature together. I want them to be together. then it'll essentially use some degree of contour detection to detect where there are contours. So if there's a significant change in pixel value from one pixel to the other, that's how it detects the contour. And the contours would basically be my coins, because I have an image with a bunch of coins and there's some background image under the coins, because the coins are placed on the floor. So I want to extract the coins, and then I want to remove the background. So the background and the coins form a contour at a pixel level. They're actually having contours. And in this case, we're going to try two different types of clustering algorithms. We're going to try k-means and discretize. And we look at both algorithms and results of both, right? This is basic code, basically for plotting my data, plotting my data onto an image. So I want to see the image, I want to see the X ticks, I want to see the Y ticks, I want to print the spectral clustering along with the model name used, all of that. So this is simple plotting. This comes from matplotlib. I'm not going to cover this in detail. And you can see that all of these items are essentially inside the for loop, with the indentation broken here. plt.show is outside the for loop, right? Everything else is inside the for loop, and this is going to run through it. We use spectral clustering. We use reshape over here, and then we have a set size for the figure. So if you change the size, it's basically the size at which you want to display the figure. This only changes the display size of the figure. It doesn't change anything much. We're also using a grayscale image, so we're going to use a CMap to grayscale, because our image is grayscale. If you did use colored images, it would be way more complex. Colored images also take a while to test, and it's not advisable to take colored images. Typically in clustering algorithms, you would make the image into grayscale and then find the clusters. If finding a cluster is all you really need to do, then the color of the image doesn't really matter, because the grayscale version of it will take into account all the colors aspects. So grayscales are much lighter to operate on. Now we're going to run through this, and you're going to notice that as soon as I run through this is actually going to take some time to give me the output. It is not as instant as you would expect, because in this case, we are actually processing an image data, and keep in mind we have shrunk the image to 20% of its size. If we had not shrunk the image, it would have taken a lot longer to do this. So I'm going to hit the run button, and you can see that it keeps showing me the star icon here, which means my result is not yet ready. And it's going through my data. It's actually running through the clustering, and you can see spectral clustering for k-means is completed. The discretize is not yet completed. K-means took 7.92 seconds. Now both are completed. So I can see spectral clustering with discretize took 5.88 seconds. So they both took slightly different times. K-means took longer than discretize. And here's my output. So this is the output of my spectral clustering. Now these colored markers that you see on the image is what we put in the plotting library. So we plotted these markers on the image. The original image is actually without these markers, right? So these markers are not on the image, but all of these gray things that you see are coins. Now keep in mind the original image could have been in absolute color, because it's an actual photograph of Greek coins that is shot. But we converted this image to grayscale. Then we also downgraded this image to 20% of its size. So we shrunk it to 20% of its size. So when you're looking at the image right now, it's pretty blurred, and you can see that it's pretty blurred, right? But it has done a good job of finding me 25 clusters. However, you can see that it did miss some points. So you can see that this region, this coin, and this coin is not actually found, right? It found the other coins, but it missed out on these two coins. And we use spectral clustering with k-means clustering algorithm over here. We can look at the output with the same output with discretized clustering. And in discretized clustering, you can see that all of my data points are properly clustered, which means it was able to successfully identify each and every coin and each and every cluster, and you can see the highlights. However, you can see at some places like the borders are off. Like you can see that the actual red highlight is a little different than the shape of the original coin. But we have done a reasonable good estimation of what the coin is like, right? So this is an example of a clustering algorithm. As you can see here, there is no right and wrong. And this is a classic example of clustering, because there is no right and wrong. You cannot use supervised learning with clustering. Clustering is primarily unsupervised learning. And what you're essentially doing is you're giving it input data. The algorithm is learning from this data, and we have used two algorithms here, the k-means and the discretize. And both algorithms have different mathematical functions. We won't be covering those functions right now, but they have different mathematical functions, different levels of accuracy. And you can also fine-tune the parameters to control the accuracy of clustering. But what we did is we gave it the data, it learned from the data, and then it tried to identify items that were most similar looking to other items inside the image. So it took the image pixel by pixel. It tried to look at it from the smallest possible pixel to as large as an entire image. And it tried to identify how many unique discrete items are actually present on this image. So it did a contour detection on all of these items to come up with the items that are most similar. And by doing so, it was able to extract all of the Greek coins for us. Right? So this is what a clustering algorithm looks like. So if you have image data of this type, the only thing you can do is cluster. So I hope at this point in time, I have been able to give you a good amount of understanding of the fundamental difference between clustering and classification. Right? And keep in mind, classification is supervised learning. We need to have known output data points to train a classification model. And this is a clustering model, has unsupervised learning. We cannot supervise it because we really don't know what we want to extract from it. So you let the model learn from itself, derive its own patterns, and give an output. Right? In the session so far, we basically use the support vector machines classification in the previous case. And in this case, you can see we have actually used the k-means clustering algorithm, and we have also used the discretized clustering example. So we've basically so far covered two rock-solid examples on classification and clustering. And in many machine learning algorithms that you do, classification and clustering is something that you will use on a daily basis. So I hope this has actually given you an understanding of why we need supervised learning, why we need unsupervised learning, and in what situations we can use one over the other. Okay, so that's all we have for today. I hope you've had something really good to take from this. We started from artificial intelligence. We went on to what is AI. Then we looked at what is machine learning. We looked at the comparison of artificial intelligence and machine learning. We also saw that machine learning is a subset of AI. Then we looked at neural networks. Then we looked at some machine learning algorithms, predominantly the classification algorithm and clustering algorithm. And then we wrote some Python programs on classification and clustering. You also now have a BlobCity cloud account, which you can use for all your future projects. So I hope I've delivered enough value to you over here for you to take something out and learn from this session. And before you go, do not forget to follow us and subscribe to our channel. That way you can stay updated about the next sessions and the newest videos that we keep releasing on our YouTube feed.